So we're going to be talking about discrete probability distributions in week number 6. We're going to essentially be constructing a probability distribution for a random variable, calculating the mean, variance, and standard deviation, and mostly talking about the expected value for this discrete random variable. Probability distribution section 6.1. So for our purposes, we say that an experiment or an observation is any process by which measurements are obtained. So for instance, you might want to count the number of eggs in a robin's nest or measure daily rainfall in inches. So it's common practice to use this letter X to represent a quantitative result, basically an outcome, of an experiment or observation. As such, we call this X a variable. A quantitative variable X is a random variable if the value that X takes on in a given experiment or observation is the chance or random outcome, which we've talked about this before. A discrete random variable can only take on a finite number of values or countable number of values. So you have to be able to count them or etc. So this word finite versus a continuous random variable. So there's a difference, and we'll be talking about this in week number 7 or next week. That's right, next week. Next week, we'll be talking about continuous random variables, but here we're talking about discrete variables. This can take on any of the countless number of values in a line interval. Now, and it's very important distinctions between discrete and continuous random variables because there's different mathematical techniques associated with the two kinds of random variables. So a quantitative variable X is a random variable if the value that it assumes corresponds to the outcome of an experiment, and usually of a random event or by chance. Usually we do note these with capital letters. The possible outcomes of X are labeled with corresponding lowercase letters, usually. So, and these would be the outcomes. So for example, the probability of, let's say, a random variable X is equal to small x, something like this, where this is the outcome, and this is the random variable. Random variable. So random variables are, again, either discrete or continuous. So this is the first thing that we have to decide. And examples of random variables, X can be equal to the SAT score for a randomly selected student. So that score, the number of people in a room at a randomly selected time of day, the number of the number on the upper face of a randomly tossed die. So we have a die. It's always great to picture things. So in most of the cases, we will consider a discrete random variable will be the result of the count. So the number of students in a statistics class is a discrete random variable, and we can have, let's say, 15, 25, 50, etc. 250 are all possible values. However, let's say 25.5 students is not a possible value for the number of students, because you can't have half a student. No, right? No. So most of the continuous random variables we will see will occur as the result of a measurement on a continuous scale. And this again is next week. So, and that is the majority that you will see. Like this is very popular, continuous, but so is discrete. So for example, the air pressure in an automobile tire represents a continuous random variable. The air pressure in theory can take on any values from, let's say, 0 pounds per square inch, PSI, to the bursting pressure of the tire. Such values, for example, these with like these decimal points, etc., and so forth are possible. And so this would be an example of a continuous random variable with like these decimal points. So let's look at some examples. Which of the following random variables are discrete and which are continuous? So measuring the time it takes a student selected at random to register for the fall term. So time is the key word here. So that would be continuous. So the next one, count the number of bad checks drawn from Upright Bank on a day selected at random. So we're counting, so that would be discrete. Next one, measure the amount of gasoline needed to drive your car this much. So this is the amount of gasoline. But what is gasoline? So this is continuous because you could have 0.5 to 30.52, like let's say liters of gasoline. Pick a random sample of 50 registered voters in a district and find the number who voted in the last election. That would be discrete. So look for keywords when you're trying to analyze if it's continuous or discrete. The probability distribution of a random variable. So a random variable has a probability distribution, whether it is discrete or if it's continuous. So both. A probability distribution is an assignment of probabilities to each distinct value of a random variable or to each interval of values of a continuous random variable. So there's features of this probability distribution of a discrete random variable. The probability distribution has a probability assigned to each distinct value of the random variable. So we have a probability assigned, and it's a distinct value for the random variable. And the sums of all the probabilities have to equal to 1. So if you add them all up, they equal to 1. And this is what we did before. So for the discrete random variable, it looks like the relative frequencies, which we've already constructed earlier. So it's very similar. So for example, we have the probabilities have to be greater than 0 and less than 1, or greater than or equal to 0 and less than or equal to 1 in this particular range. And they have to sum up to 1, which we remember this earlier. Let's look at an example. Excuse me, let me have some water. So Dr. Mendoza developed a test to measure boredom tolerance. He administered it to a group of 2,000 adults. So that's how many people, let's call it N, between the ages of 25 to 35. The possible scores were 0, 1, 2, 3, 4, 5, and 6. So 0 is when you're like, 6 indicates the highest tolerance. So this is like you have a tolerance. This is like basically no tolerance. And then you have a square between it. And these are the numbers of subjects. You can add this up and you would see that you get 20,000 people. You can pause the video and just add it up and make sure. Now, if a subject is chosen at random, what is the probability that he or she will have a score of 3? Well, here we see that it's 3, and you have 6,000 people, subjects, scored a 3. So it's just going to be, of course, that probability is going to be 6,000 over 20,000, which is 0.3. And we could convert it to percentage if we wish. In a similar way, we can use these relative frequencies to compute the probabilities for the other scores. And you could add up the probabilities and you see that you get 1. So it's similar to what we did. These probability assignments make up the probability distribution. And we notice that they're mutually exclusive. So no one subject has 2 scores. The sum of the probabilities of all the scores is 1. So the graph of this distribution is just simply a relative frequency histogram. You can see like the scores here are plotted on the x-axis and the probabilities are on the y-axis. It doesn't have to start like at 0 because we have a value at 0. So we put like this little dash here and we label it. So it's basically a bar graph that we've done before with 1 unit wide. And the area over the bar graph of a score equals the height and thus represents the probability of that score. Since the sum of the probabilities is 1, the area under the graph is also 1. So all this area is, so if you sum it up, it's going to be equal to 1. That's a 1. So let's say the top-notch clothing company needs to hire someone with a score on this boredom tolerance test of 5 or 6 to operate the fabric press machine. What is the probability a candidate selected at random will meet this criteria? So 5 or 6, so it's mutually exclusive, so there's no overlap, so we can separate out the probabilities, and we can just simply add up those probabilities and we get our answer of 0.10, which is 10%. So you can always go back on this chart. So 5 or 6, you can read it off the chart, or you can read it off of the table, the 5 or the 6. These two together, you add them, and you would get our final answer. So you notice that to find the probability of 5 or 6, you simply just add the areas of the bars over 5 and over 6. So you can read it from the chart, or you can read it from the table, either way. So either chart or table. So a tool for cryptanalysis, so this is basically that science of code breaking, is to use relative frequencies of occurrence of letters to break the codes. In addition to cryptanalysis, creation of word games also uses this technique. Oxford Dictionaries publishes, so this is actually very interesting. I audited a course just a week when I was an undergrad, and they actually looked at the frequencies, the relative frequencies of various messages and being sent and things like that. And we kind of played a game of different ways of breaking codes that I remember. Anyways, I digress. Back to the question. So they did this analysis of letter frequencies and words and listed in the main entries of this concise Oxford Dictionary. So suppose Langley took a random sample of 1,000 words occurring in this crossword puzzle. So we have 1,000 words. And this table in the next slide shows the relative frequency of the letters occurring in the sample. So from A to Z, we had counted how many occurrences of these letters occurred in 1,000 words. And we could add up the frequency, and you should notice that it's over 1,000. So we can find those probabilities that we obtain the letter A would be 85 over 1,000. So this is the frequency over the total, which is 0.085. Then we could do the next letter, etc. Do the probabilities all add up to 1? Yes, they do. I think you should just pause the video here and add them up and check. Then we could do the next one. E would be 112 divided by 1,000. Next one would be 0.075, 0.072, and the next one, last one. Now, if you select at random from the crossword puzzle, what is the probability the letter will be a vowel? So A, E, I, O, U are vowels. So we would add up like those probabilities of like those vowels. And since you can't have an A and an E, they're mutually exclusive. So we would add them all up. And you would, you notice when we look at the probabilities of the vowels, we see that they're mutually exclusive. So we can write them this way, and we just add up those probabilities, and we see we get 0.38, which is 38% that you would get a vowel if you select at random from a crossword puzzle list. So a probability distribution can be thought of as a relative frequency distribution based on a very large n. As such, it has this mean and a standard deviation. If we were referring to the probability distribution of a population, then we use the Greek letter mu for the mean and sigma for the standard deviation. Remember that. So when we see the Greek letters used, we know the information given is from the entire population rather than just a sample. So if we have a sample probability distribution, we use X bar and S respectively for the mean and standard deviation. So this is again for the sample. And this for the population is these. So it's just about remembering the notation. So this is also a reminder. So remember when you toss tails with a balanced coin, a half, so the probability that you get a tail is a half. The probability that you draw an ace is, well, there's 4 aces out of 52 cards. The probability of either rolling a 3 or a 5 is going to be, well, the probability of 3 or a 5 rolling at once. This is fair, a sided coin. Sorry, that should have been R, is 2 over 6. And rolling a total of a 5, let's say with a fair pair of 6-sided die, would be 4 over 36. So let's look at this example. So we would write 1, 2, 3, 4, 5, 6. And on this side, let me erase this part. Of 1, 2, 3, 4, 5, 6. And then we sum them up because rolling a 5, so it means like a sum. So this would be 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. And you see that if we rolling a total of 5, so we can get 5 here, 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 here. So we get 5 4 times out of the total would be, well, 6 times 6, which is 4 over 36, which is that answer. So it's just about finding that probability of the sum is 5, is 4 over 36. Now let's look at this example. It's quite kind of interesting. Suppose you have 2 socks are selected at random and removed in succession from a drawer. And so suppose you have 5 brown socks. Let's pretend they're blue. 1, 2, 3, 4, 5. So we have 5 of them. And we have 3 green ones. So 1, 2, 3 green socks. We could actually draw a sock. But anywho. So let's find, and we know our sample space. So you draw one, you can have brown, brown, or the first one can be brown and the second one can be green, or the first one can be green and the second one is brown, or green, green. So you have like these possibilities. Let X be the number of brown socks selected. So we're looking at the amount of brown socks that we do select. So that is what we're interested in. And for these purposes, you can think brown is blue because they both start with B's. So it might be easier. So the number of brown socks selected is called this thing called the range, if you remember. So that you see that the range, you can have no brown socks selected, 1 brown sock selected, or 2 brown socks selected. So it goes from 0, 1, and 2 are possibilities. The probability of a brown and a brown would be, well, your first sock selected is going to be brown. So 5 divided by the total, 5, 6, 7, 8, times the next one. Well, 1 is removed. So now we have 4 divided by 7 in terms of the brown socks. Probability that you get a brown sock first and then a green. Well, that is, you select 1 brown sock out of the total is 8. And now we select a green sock. So you have 3 choices there out of 7. What about the probability of a green sock and then brown? Well, that would be the green sock. You have 3 choices out of 8. And then we have 5 choices out of 7. And the last one is the probability of green and green. Well, you have 3 choices out of 8. And then you remove 1, and you have 2 choices out of 7. So like you see our probabilities. Now, we see the probability of getting brown would just be 20 over 58. And no socks or green, just no brown socks, just green socks would be 6 over 56. But you have 2 options essentially, here and here, to get essentially just 1 brown sock. So you would add these together. You would add 15 over 56 plus 15 over 56 to give us 30 over 56. So there's 2 possible ways to obtain essentially 1 brown sock. Section 6.2, mean, variance, standard deviation, and expectation. So the mean and standard deviation of a probability, population probability distribution are as follows. And this is essentially related to the weighted mean. So remember, the weighted mean is just like we have X times a weight divided by our weights. Here, if we exchange our weights for our probability, we see that this denominator, because the probability distribution has to be, this is equal to 1. So this whole thing is our answer. So this is how we actually calculate it. Now there's an additional formula for the standard deviation is just the square root of the sum of x minus mu squared times that probability. And this is basically called the standard deviation of x. And you can see P of x is the probability of that distribution. And this is, we sum it up over all the values. And again, note that if it's mu and standard sigma, if we're talking about the population means. So this is why we use this particular notation. So the mean of a probability distribution is often called this thing called expected value, which is what we're going to be focusing on of the distribution. So this terminology reflects the idea that the mean represents a central point or cluster point for the entire distribution. For, of course, the mean or expected value is an average value, and as such, it need not be a point of the sample space. The standard deviation is often represented as a measure of risk. So risk, if you see standard deviation, and a larger standard deviation implies a greater likelihood that the random variable x is different from the expected value mu. So let's look at an example. As we are influenced to buy a product by ads we saw on TV, are we influenced to buy a product? So suppose we had like this data and it's in a chart, and 5 or more, basically we treat it as 5 in this example. This is why we have an asterisk. So the number of times a buyer sees an infomercial or an ad on TV and the percentage of buyers. So we can have this data. We can treat this information as basically an estimate of the probability distribution because the events are mutually exclusive. Either watch it once or twice. Actually here, and we grouped it all together, but we're still treating it as mutually exclusive. And the sum of the percentages is 100%. We can add them up and check this. Now, how to compute the mean and standard deviation of the distribution? Well, we can compute those probabilities. They're just given here. We just make them out of less than 1, between 0 and 1, the probability, the percentages, turn them into a number between 0 and 1. Now we can calculate 1 times this probability plus 2 times this probability plus 3 times this probability plus 4 times this probability times 5 times this probability. Then we add them all up and we get 2.54. Great. So that is our expected value. So we have that number now. So that's how many, so back to this question. So if you see about 2.54 is the expected value of times you would expect to watch essentially an ad. So we expect the person buying the product to have seen 2.54 ads. Now, once we have this number, we can take the number of viewings, x, subtract our mu, calculate these numbers, x minus mu, and then we can square that column. Then this column times this probability will give us our last column. Then we sum it all up and we take the square root and we obtain 1.367 is our standard deviation. So this is how you calculate standard deviation and the mean. At a carnival, you pay, let's say, $2. And I love like these kind of questions to play a coin flipping game with free fair coins. And perhaps you've gone somewhere and you've tried as a kid to play one of these games. So on each coin, one side has the number 0 and the other side has the number 1. So you flip the 3 coins at one time and you win $1. So you get $1 for every one that appears on the top. And so are your expected earnings equal to the cost to play? What are the 8 equally likely outcomes for throwing the 3 coins? Well, we did this before. So you can either have all 3 coins be ones, or some can be all zeros, or a combination. And we know how to create that sample space. So let's count now. Let's complete this. So it's possible that you have no ones. So you basically kind of lose 1 1, 2 ones, or 3 ones. So the frequency that this would occur, that you would receive none, would be 1. The frequency that you would receive 3 would be 1. Now, the other 2 would be 3 and 3. We could go back and you could count. You could go 1 1 0 1 1 1 0 1. That would be 1 and 1, and this one. So there would be 3 of those, and 2 ways of getting the ones, and 1 way of getting 1 1, and the other 2 would be zeros. So we can compute these probabilities, and we see that this would be 1 over 8. This would be 3 over 8. This would be 3 over 8. This would be 1 over 8. Now we can take this probability, multiply it by x, and get 0. Here would be this number, and this number. Next, you see that this sums up to 1. And so now we're going to determine the expected value by finding the sum of the appropriate column. So once you sum up the last column, we see that it's equal to 1.5. So that is our expected value, is to obtain, if we play this game, $1.5. But we remember, we paid $2. So if we expect to earn $1.5 and it costs us $2 to play, you're going to lose this game. Going to lose. So this is the idea of kind of like the casino. The house kind of wins in the long run. So here's an extra example. So toss 2 fair coins and define x as the number of heads. So you can have head, 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 tail, tail, head, tail, tail. So there's a probability each has like 1 over 4, basically occurring. But how many, we're defining x to be the number of heads. We can have it capital X or small x. Oh, no, like those are, 1 second. So like these are the outcomes. So here we see that we have 2 heads, 1 and 2. Here we have 1 head, and no heads. Now we can find these probabilities. We see that the probability of no heads is 1 over 4. The probability that you would have 1 head, well, either head, tail, or tail, head. So that would be 1 over 4 plus 1 over 4 is a half. Or the probability that you have 2 heads, well, that would be 1 over 4. So we can calculate that probability column. And that's what I wrote. Then we can also have graph it, doing a probability histogram, which we've done before, where we have 0, 1, and 2, and we draw like this histogram. So let's say we're tossing a fair coin 2 times and record the number of heads. And we have like this chart. So we have the probability. Once we have like these probability and we have our x's, we can multiply x by our probability. So 0, because 0 times 1 over 4 is 0. 1 times a half is a half. 2 times 1 over 4 is a half. And we can sum this column up, sum it up, and we get 1. So this makes sense. Now, once we have, this is our 1, x minus 1, and then we square it. So -1 squared, that's positive. So this becomes 1 over 4. 1 minus 1 is 0. So this goes away. 1 squared is 1 over 4. We add them up, a quarter plus a quarter, and we have 0.5. So that's our variance. And then we take that square root and it's 0.71. The probability distribution for X is the number of heads in tossing 2 coins. So we can draw like this probability, and we see, of course, okay, the mean right here is 1, and the spread, how far it spreads out, is 0.71. And we see, of course, it's mound shape and it's symmetrical, which we're used to. So let's see more examples. So toss a coin 3 times, 1, 2, 3. So we can create like this is a sample space. We've done this before where we have like tail, head, tail, head, tail, head, tail, head, tail, head, tail, head, tail, head. And we have our sample space. We see that the number of heads ranges. You can have no heads, 1, 2, or 3. So that is the range. And we can see that the probability essentially of getting no heads is just the probability of tail, tail, tail. The probability of getting 1 head is going to be, well, 1 head would be tail, tail, head, plus probability of head, tail, tail, plus the probability of tail, head, tail, which is 1 over 8 plus 1 over 8 plus 1 over 8, which is 3 over 8. The probability of 2 heads, so head, head, tail, plus tail, head, tail, head, plus tail, head, head. Again, it's the same thing. It's 1 over 8 plus 1 over 8, which is 3 over 8. And the last one is the probability of head, head, head is 1 over 8. Multivariate distributions, 6.3. So we now consider the case when 2 or more random variables are defined on the same joint sample space. So we start with this bivariate case, that is when 2 random variables, X and Y, are defined for a common sample space. So for example, X could be the sum of rolling 2 dice and Y could be their product. So this is how we write the particular case. Probability of X, and this is the outcome, and these would be the outcomes for these random variables, X and Y. And this would be the intersection of the events. So if X and Y are discrete random variables, then this function, we could write this function like this, for each pair of X and Y in the range of X and Y. And this is called the joint probability distribution of X and Y. A bivariate function can serve as a joint probability distribution for a discrete random variable, X and Y, if and only if this function is greater than or equal to 0. And this is first where you hold X and you sum up over Y, and then you move on to the next X, and then you sum up over Y, and if this is equal to 1. So let's look at an example. So verify the theorem for the following. So we can just add them all up and we see that it is equal to 1. So 6 plus 12 plus 3 plus 8 plus 6 plus 1. This is all equal to 36. And they're all over 36. So 36 over 36 equals 1. So yes. So these would be your X values, and these would be, let's say, your Y values. Sorry, I forgot to write that. Mathematical expectation, section 6.4. Suppose you are at a casino. Yay, you're at a casino that has, so this is a fun example, that has this dice game which costs $1,000 for a single roll of a two six-sided die. Ooh, that's expensive. You win $5,555. Wow, by rolling a 7, and you lose your money otherwise. So then you lose. Do you think it's worthwhile to play? So let's first think about it as you roll some dice. So again, I'm going to write this out for you. And then we can sum them up. So 2, I'll just say, where is it a 7? So you can write 6 and a 1. That will give us a 7, 7, 7, 7, 7, 7. You can fill out the rest here. So you see that only here can be, so 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6. So 6 possible ways to roll a 7 out of 36 possibilities. So this is reduced down to 1/6, essentially. Okay, so we have 1/6. That is the probability of rolling a 7 is 1/6 because it's similar to 6/36 reduced down. Not rolling a 7 would be all the other options out here. And if you counted them up, there would be 30 divided by 36 or 5/6. So how do you use this expectation? So the expected value would be that probability times your outcome. So here the outcome is $5,555 times the next probability times that outcome, which is 0, because you only have 2 options. You either win or you lose. So this is you win, and this is you lose. Boo. So let's not lose. So it's this number. So this goes away, and you see you get $926, but you paid $1,000. So you're going to probably lose in the long run if you keep playing. This is why the house always wins. So if X is a discrete random variable and f of X is the value of its probability distribution at X, the expected value of X, or the expectation of X, is defined by this. So the expected value of X is equal to the sum of X times f of X. And this could be our probability distribution, like P of X. And you can define your own probability distributions. It doesn't have to be something that it can be anything, actually. It can just be a function. So where the sum is over all X in the range, the sum must be defined in order for the expected value to have this meaning. So this is our previous example. So in the example, the random variable X is the amount of money won on each roll. So this range of X is basically the outcomes. So you can either lose, or you can win, lose. Let's draw pictures. So since the probability of rolling a 7 is 1/6, we have this is our probability, and the probability of losing essentially is 5/6. So you're ended up with this expected value. So the analysis shows that this is a losing game because our expected value is less than the cost to play. In the long run, we expect to lose money. Multivariate expected value. Now, suppose X and Y are random variables with joint probability distribution, or this density function f of X. Then we can define the Z to be equal to G of X, Y, and it's also a random variable defined by this function G depending on X and Y. Expected value of Y may be computed in this following way. So with the notation of above, if x and y are discrete random variables, then we can basically plug in this g for our x before, and we have it as the sum of y, the sum of x and the sum of y over g x of y times f of xy. So the sums are basically taken over x and y in these ranges of x and y respectively. So let's say we have z is equal to x plus y, then z is a random variable which gives the total number. What is the expected value? And like this is our x here, this is our y here. I don't know why, sorry, this should not be bolded. So we can just basically substitute it. And this also helps us do things, the expected value of x squared and various things. But here we have x plus y. So we substitute that in for like this function. So we first hold x to be 0, and then y is 0. So that would be 6 over 38. Next one is, this is our x and this is our y. And y now moves up to 1 here. So that would be 8 over 36. Again, then y moves up to 2 and we have 1 over 36. We've exhausted our y's. So now we move up x to 1 and y is 0. Plus x and y, the next one is 6 over 36 plus the last one. So that it would be our expected value is something like this.